Welcome back to our third episode. Just to recap, in the first episode, we talked about these concepts in engineering and related to engineering. The previous episode, we looked at power, energy, and force. Do know I started off with a little bit of a mistake there, but that's okay. You can watch the video again. And in this third episode, we will focus on force and torque. And again, this is not meant to be a replacement for a physics class, but I think it's important at least to know of the concepts so that it's not completely new to you when you have to encounter it. So let's take a look, talking about forces and torques, and this will be a nice segue to the next episode where we'll talk about simple machines. So let's just take a look at Newton's laws of motion. Okay, I'm just going to sort of state it, and then we'll talk about a little bit about what it really means. So the first one, body will remain at rest or moving at a constant velocity unless it is acted on by an imbalanced force. And so that's sort of the example of if you're in space. Okay, there's sort of the ideal, not really much friction or air resistance. So object in motion will stay in motion, object in rest will stay at rest. And a good way to just understand this intuitively is if you roll a ball across a floor, eventually it's going to stop. It's either going to stop because it hit a wall, or it's going to stop because the friction and air resistance across that ball will cause it to slow down. Okay, the second law, the sum of the forces on the object is proportional to the object's mass and its acceleration. And so we often say in static analysis, all right, really you set the forces equal to 0. So if you have an object here and you apply a force this way, all right, up until the point that it moves, it's not moving. I know that sort of sounds funny. And that's because there is an opposing frictional force. All right, and again, I'm just going to throw some formulas out here. This is proportional to the coefficient of friction mu and the normal force, which is actually acting upwards this way. Anyways, you push F, okay? F starts from 0 and it goes all the way up to F. And the moment that it can overcome that frictional force, then it's in motion. Now, again, a bit more of a nuance here. We say that F equals ma. So if it's moving at a constant velocity, all right, the velocity v is not changing, so it can be in motion, but the acceleration just is 0. Okay, so again, just trying to get you to see these higher level concepts. And then lastly, equal and opposite force. So I'll just read this out to you from a website. If two bodies exert a force on one another, the forces are equal in magnitude but opposite in direction. And sort of the normal example is if you have this block, or even if you have this person here on Earth, that you have a force that is the force due to gravity, but you also have a normal force. Okay? So that's Newton's laws. And what I want to also talk about is this idea of torque. And this torque, think of torque as adding another dimension. So if we start off, we just have this block and we're applying forces and it's only moving in one dimension. In a typical physics class, you also talk about projectile motion. So if you have the x and the y and you're launching out this object, it starts off with some initial velocity, and then there are these kinematic equations to see how it moves. Okay. Torque is very important because it then introduces the idea of rotation. So in your one-dimensional motion here or two-dimensional kinematics, you're assuming, let's say you have a more, let's say, odd shape here. Okay, this is its center of mass or center of rotation. You're assuming that this does not change orientation. All right, but we know in reality that things will rotate. Of course, if you have something that's perfectly symmetric, rotationally symmetric, then maybe you can't see it rotate. But usually things will rotate. And so let's just think about a ruler. And if you fix the ruler on one end. We would call that a pivot. Sometimes we call it a fulcrum. All right? If you apply a force this way, what do you know will happen? All right? You know that it's going to rotate, and it's going to rotate this way. Now, if you remember in our previous episode, we talked about applying a force here, right? Let me draw this again. You have a block, you apply a force, F, and then it moves some distance, D. Right? You remember that? And we say if we moved it through that distance, D, we've done some work on it. Force times that distance, okay? And then the question of how fast can we do it? If we do that over a certain time, then we'll get power, right? You remember that. Now in this case, this is different, although it might seem similar at first. Let's say there's a distance D, all right? And the letters that people use, they use different conventions, but let's just do D for now, just to sort of show you the potential confusion. You have a distance D, and you notice that in this case, the direction of the force applied is in the direction of the distance moved, yeah? But here, okay, sometimes this ruler, they call it a rigid body, all right? And this is really important because rigid body means it doesn't bend. And in higher levels of analysis, then things do bend. Anyways, you apply a force and you have this distance. If we just sort of draw this out, we call these vectors. Again, more terms that you might encounter later on. Right? You have force, you have a distance. Right? In order to calculate the torque, and they use this Greek letter tau for torque, then it is that distance times the force. Now, this is a little different. It's still Newton meters, but we actually treat that, and I've actually sort of swapped out the units here, as its own unit. And that, explaining why that is, that's sort of beyond the scope of my intent in these videos. But just know that when you apply a torque, you're applying a force that is perpendicular to that distance. Now, we know that if you applied a force, let's say this way, let's call this, let's see, what's a good letter? I don't know, P. If you applied a force that way, it's still going to rotate, but it's not going to rotate as much as the force straight on it. That's actually where we would decompose this force P into the component that is 90 degrees, and again, that's sort of more advanced things. So key thing to remember, and let's maybe finish off with a very classic example of the seesaw, okay? If you have a block here, and you have a block here, in this case, the fulcrum, the pivot, it's not at the end, it's in the middle. So let's say the weight is W, okay? And the weight here is, let's say, V, okay? In order for it to be balanced, we have to look at the amounts of V and W, and also the distance, okay? So let's actually use some numbers just for intuition here, and I'll draw it somewhat to scale here. All right, so let's say you had a V, and you have a W. And let's say that you have a distance, two distances, D sub V, and we use these subscripts just to sort of see what it's associated with. Okay. In order for this to be balanced like this, we have the intuition that W times D sub W must equal to V times D sub V. So let's say that the weight W is 2 times V. So we can substitute this in. All right, here's where we do a little bit of math. 2V times D sub W equals V times D sub V. So if we want to know what this distance is in relationship, we can divide by 2V, and we must know, or we know that the distance between the fulcrum and the weight must be half of the distance between this and this. And that's just something we know intuitively. And this is an example of torque. All right, I think that's enough for this episode. And in the next one, we'll talk a bit about simple machines.